discussion session for those of you who want to continue the discussion. So, but let's now continue with the next speaker, who is Zohar Komargodski, and he will talk about highest central charges and gapped boundary.
Unmute and share, right? Okay.
Okay, Zohar, please go ahead.
Thanks so much to the organizers for this magnificent event, from which I already learned a lot, and I think it's extremely well organized, and also for letting me present this work in collaboration with Justin Kaidi, Kantaro Mori, who is now in Tokyo University, Sahan Saif-Nashri, who is my student, and Chuheng Shao, currently at the IES. So let me just start with a very slow review. We've known for 40 years or so from the work of Alvarez, Gomes, and Witt that 1+1 dimensional systems are forced to be gapless if the chiral central charge is non-vanishing. I will refer to this combination as the chiral central charge throughout this talk. But from a modern perspective, when we think about 1+1 dimensional dynamics, we have to distinguish two cases. One is when this chiral central charge is a multiple of 8, and it's possibly non-zero. Then the terminology nowadays would be that this system has a gravitational anomaly, but it's of the 't Hooft type, a 't Hooft gravitational anomaly. So a 1+1 dimensional system with a non-vanishing chiral central charge is not invariant under diffeomorphisms. But the type of non-invariance under diffeomorphisms should be distinguished between two cases. One is when the chiral central charge is a multiple of 8, and the other when it's not. So when it is a multiple of 8, the non-diffeomorphism invariance of the 1+1 dimensional theory can be ameliorated or cancelled by adding an auxiliary bulk system, which is 2+1 dimensional. So in particle physics, we think about it as an auxiliary 2+1 dimensional system. In condensed matter, it's often a physical system. So in this 2+1 dimensional space, we should add something in order to fix the non-diffeomorphism invariance of the 1+1 dimensional system. And if it's a multiple of 8, we only have to add the gravitational Chern-Simons term in this 2+1 dimensional system, and that's it. It's just a classical field theory in 2+1 dimensions. It's not a quantum field theory, just a classical field theory. So that's the situation of a 't Hooft gravitational anomaly. However, if the chiral central charge is not a multiple of 8, the non-diffeomorphism invariance cannot be cancelled by adding a classical field theory in 2+1 dimensions. And such theories are nowadays called relative theories. So in order to cancel the non-diffeomorphism invariance of the 2+1 dimensional system, of the 1+1 dimensional system, we must add a non-trivial physical quantum theory in 2+1 dimensions. This quantum theory in 2+1 dimensions ought to be either a gapless theory or a non-trivial topological field theory in 2+1 dimensions. So this sort of non-diffeomorphism invariance of a 1+1 dimensional system is much worse or much more constraining than this one. Now, let me just review a very classic example from condensed matter theory. Condensed matter theories have come up with the quantum Hall effect, in which we have a chiral mode on the 1+1 dimensional boundary, which has chiral central charge 1. It's just a chiral compact boson. And this is the boundary of a non-trivial topological field theory in the bulk, which is a U1 level K Chern-Simons theory. So this is a nice example of a relative theory. Because the chiral central charge on the boundary is not a multiple of 8, we cannot cancel the non-diffeomorphism invariance of a single chiral boson by adding a classical field theory. So we're forced to add a topological field theory in the bulk, and this is, of course, the claim to fame of the quantum Hall state. An example which is a little bit more standard is 8 chiral bosons moving on the E8 lattice, for instance. This is a system of just 8 chiral bosons, so it has a chiral central charge 8. And actually, this system does not require a 2+1 dimensional bulk, which is dynamical. We just need a classical field theory in 2+1 dimensions, and we can cancel the gravitational anomaly. So the topic of this talk would be the very general question of given a 2+1 dimensional topological field theory, we might have edge modes, like in the quantum Hall effect. But the question is, can it be that the edge modes cannot be lifted, cannot be made gapped, even if the chiral central charge is vanishing? And the answer is non-trivial. Let me give you an example. Consider U1 level k times U1 level minus k prime Chern-Simons field theory in 2+1 dimensions, for which I wrote the Lagrangian here. This theory, because it has a k and a minus k, so the total chiral central charge vanishes. And if you're just a very naive physicist, like I was up until a few months ago, you might think that there must be a way to gap the boundary, because the chiral central charge vanishes. The boundary, namely the edge modes, have no diffeomorphism anomaly. And since there is no diffeomorphism anomaly, why would there not be a way to gap the boundary? But the answer is non-trivial. The answer is that there does not exist a way to gap the boundary unless a very strange number theoretic condition on k and k prime is satisfied, namely that kk prime is a square of a number. And if it is a square, you can define gapped boundary conditions. So this Chern-Simons theory is the simplest example, as far as I'm concerned, of a system that has a boundary that is fully gravitational diffeomorphism invariant. There is no 't Hooft anomaly, but there is a funny restriction, which if it's not satisfied, the edge modes would be protected and gapless. So there's no way to get rid of the edge modes in this theory unless this funny condition is satisfied. So the example I've just given is for an abelian theory, but there are plenty of non-abelian examples. Let me just mention a very esoteric non-abelian theory, which is the Fibonacci enyons. Actually, they appeared in several talks already today. This is just G2 level 1 Chern-Simons theory. It has a chiral central charge, which is fractional. It's 14/5. And clearly, it leads to a relative theory on the boundary with gapless edge modes. But if you take 20 copies of it, then the chiral central charge is divisible by 8. And you might think that you can gap it out now because the chiral central charge, because now there exist boundary conditions with vanishing chiral central charge. But it's not true. In fact, there is a theorem that no power of G2 level 1 has a gapped boundary. Another thing that I want to say before I get into the actual content of this talk is that there is some connection between the question of gapped edge modes and interfaces. So if two topological theory have an interface, there is a famous folding trick in which you bring T2 over T1 while you reverse the orientation of T2. So the question of the existence of gapped or topological boundary conditions for T1 times T2 bar is equivalent to the question of gapped or topological interfaces between T1 and T2. These are identical questions. And mathematicians, including these very nice and influential papers, have defined a group structure, which is like the right language to think about gapped boundaries. So the group structure is that if two theories, T1 and T2, are such that T1 times T2 bar has a gapped boundary, then we might declare these two theories to be equivalent. This defines a group, which is called the Witt group. It's an abelian group, and you can study it. This group has something to do with with gapped or topological boundary conditions because of this folding trick. So these two subjects are related, though not identical. So this leads me now to introduce the main topic of this lecture. Are there additional chiral central charges that we're unaware of that would explain why some Chern-Simons theories lead to boundary conditions with fully diffeomorphism invariant edge modes, but they cannot be gapped? That sounds like an anomaly, that you cannot gap something. Maybe there is a new anomaly. So the essence of this talk is about whether there exist new obstructions or some nice obstructions to gapping the boundary other than the chiral central charge. So we're asking if there is anything beyond the famous gravitational anomaly of Alvarez, Geom, and Witt. Of course, this subject is of relevance to several communities, and given that I only have 15 minutes left, probably, I won't be able to cover all the points of view, but I'll give you a flavor of what kind of arguments we use in the upcoming paper to attack this problem. So the central idea is the following. This is perhaps the most important idea. So if a topological field theory has a gapped boundary, you can think about this gap boundary as a topological boundary. Now, what does it mean for a boundary to be topological? It means that you can move the boundary without changing the partition function. There is no displacement operator response theory for the boundary. And this leads to far-reaching consequences that you will see. So let's take any topological field theory and carve out a cube. And on the boundary of the cube, we'll put our gapped boundary conditions. Now, because gapped boundary conditions and topological boundary conditions are the same, you can shrink the cube without changing the partition function. This is not true for the chiral. This is not true if there are chiral edge modes on the boundary. Then shrinking the cube would change the Casimir energy and it changes the partition function. But if the boundary of the cube is gapped, you can shrink it without paying any price. And now that you've shrunk it, you can replace this cube by a linear combination over anyons with non-negative integer coefficients. That's because a very thin object in Chern-Simons theory must be a combination of anyons, because the anyons give a complete set of the superselection sectors of the theory. And so the existence of a topological boundary is equivalent to the existence of a very special linear combination of anyons that's equivalent to that gapped or topological boundary. And so the whole point is to try to understand what are the restrictions on this very special enyon that I will call curly A, which exists only if there is a gap/topological boundary. So the first thought experiment you can do is to consider the annulus, putting the Chern-Simons theory or the topological field theory on an annulus. And in the inside boundary, you can put this special enyon or the gapped boundary conditions. And on the outside, you'll put the famous chiral algebra, rational conformal field theory boundary conditions of Elitzur, Moore, Schwimmer, Seiberg, and anticipated, of course, by the work on Jones polynomials by Witt. So by shrinking the interior, I'm doing the same trick now of replacing this special boundary condition by a sum over anyons. I get a sum over chiral characters. So the existence of a topological boundary / a gapped boundary from the two-dimensional rational conformal field theory point of view is completely equivalent to the existence of a holomorphic modular invariant. And this is very constraining from the two-dimensional point of view. It leads to the fact that this linear combination of anyons has to be invariant under the S matrix in some sense, and it has to be invariant under the T matrix, and it leads to a constraint on the quantum dimension of this very special enyon curly A. So it leads to a bunch of algebraic constraints that you can put in the computer. The way to say it from the rational conformal field theory point of view is that the chiral algebra can be extended to have one character. So it's something that can be implemented almost algorithmically on the computer. And if you were to do this exercise for U1 level k times U1 level minus k prime or the Fibonacci enyons, you would see that there is no solution. For theories of the type T times T bar, which is a theory in its time reversal, of course, there must be a gapped boundary, because by unfolding, there is a trivial interface. And you can find an explicit expression for this very special enyon A, which is equivalent to this bubble of nothing cube curly. So there you can find it explicitly. It's one of the only examples where there is a general explicit expression. Now, for abelian theories, this constraint immediately implies that the total number of enyons must be a complete square. And that explains why KK prime had to be a complete square in our U1 example at the beginning of the talk. So from these considerations, you can immediately derive that for abelian theories, the number of enyons must be a complete square. Otherwise, there cannot be. Sorry. So in addition, you can derive that for abelian theories, this curly enyon A is comprised of generators of an anomaly-free one-form symmetry. So these are some particular things for abelian theories. And this connects to some developments in the subject long ago, like a decade ago, by Kapustin, Saulina, very nice works by this group and the condensed matter people and many others. So for abelian theories, what I've said so far can be shown to be completely equivalent to the existence of an anomaly-free one-form symmetry. Now, it could be that there is more than one anomaly-free one-form symmetry group of the right dimension. And for instance, this appears in the low energy limit of the toric code that Chu-Heng mentioned. But I won't get into it for lack of time. Now, the gapped boundary that you can obtain in theories where this curly A, special enyon A exists, is you should think about it as condensing this enyon. And for abelian theories, we understand what it means to condense an anion. It's the same as gauging a one-form symmetry. Here, I just want to emphasize that for non-abelian theories, while everything I said so far is true, namely that the existence of this Cayley anion A is what you need to have a gapped boundary, what it physically means to condense A is not as clear. And Chuheng referred to it at the end of his very nice review talk. These are some papers that he also cited in the end of his review talk, trying to understand what it might mean to condense a non-abelian anion A. There is no clean path integral interpretation yet. So now let me get to the main, summarize the main results in the last 5 minutes. The chiral central charge famously appears in the three-sphere partition function. And it's an obstruction to having a gapped boundary. This is the gravitational anomaly of the edge modes. So the main point is that there exists many other chiral central charges, which are likewise obtained from partition functions on some three manifolds. They are the phases of some partition functions on three manifolds. So this is a central theorem that you can prove, that a gapped boundary for any topological quantum field theory, whether it's abelian or non-abelian, implies that the partition functions on length spaces with index n are positive numbers without phases, as long as this GCD condition is satisfied. Now, NFS is the Frobenius-Schur indicator. It's essentially the order of the T matrix, or more physically, the spins are some roots of unity. Thetas are the exponentials of the spins. There are some roots of unity, and this is the minimal integer, such that all these powers are 1. So there is a series of length spaces. If you were able to compute their phases through this formula, the phases of these partition functions, you would find very nice necessary conditions for the existence of edge modes, which are massless. So this provides essentially a list of higher central charges, of which the chiral central charge is the simplest example, which you obtain by plugging n equals 1. And these are all non-trivial obstructions to gapped boundaries. You can check that they work in examples. You can ask if this list of new chiral central charges is complete, namely if it's a necessary and sufficient condition. So in general, the answer is no. But for abelian theories, we found a slight enlargement of this list of new chiral central charges, which are complete. So they're necessary and sufficient. So instead of just looking at the length spaces with index n that satisfy this condition, you can look at length spaces satisfying a slightly more general condition, and you can prove that this is complete. So given any abelian theory, you fit it into this machine, and this provides a necessary and sufficient condition for having protected edge modes, even if the chiral central charge vanishes. I'll finish with listing just a few fun facts. So you can prove that every abelian theory, if you stack it 8 times, you take 8 copies of it, it always has a gapped boundary. This is a mysterious correct result. However, as I said at the beginning, some non-abelian theories do not enjoy this property, and any number of times you would stack them would still not lead to a gapped boundary. There is also a curious symmetry that we have found in abelian theories between the K matrix and the linking matrix, which defines the surgery manifold. I won't talk about it, I have no time, but it sounds like it's related. It can be understood through the 3D correspondence. In fact, many things that we found look like they could have a geometric interpretation from the 3D correspondence. And finally, a fun fact that is useful to remember is that it's easy to prove from this formalism that every abelian theory that has a gapped boundary is actually a discrete gauge theory, a discrete abelian gauge theory, and vice versa, every discrete abelian gauge theory has a gapped boundary. That's not true for non-abelian theories. So just let me conclude. There is a list of very natural generalizations of the gravitational anomaly chiral central charge of Alvarez-Gomez-Witten. They're computable. This list is computable. We know we have a formula for these chiral central charges like this. These are the phases of this combination, where theta are the spins and d are the quantum dimensions of the anyons. And they provide rigorous obstructions to having a gapped boundary. To prove that this is true, you must study properties of this anion curly A. And so this is a natural extension of the chiral central charge, which would be nice to understand better. I'll now quickly go over 5 questions that remain open. So as I said, for non-abelian theories, we were not able to find the complete set of chiral central charges, complete in the sense that it's necessary and sufficient. So we have not been able to do that yet. But for the abelian theories, we've succeeded. So it would be nice to complete this program for the non-abelian case. Also, another thing that I mentioned in passing is that sometimes there is more than one gapped boundary condition, such as in the Z2 gauge theory. It would be nice to count them. There is also a very interesting and canonical question about the interplay between boundary conditions and symmetries. So even if some theories have gapped boundary conditions, if you want to preserve some symmetry, you might not have any gapped boundary condition. So it would be nice to understand if this can be, these obstructions can be measured by some yet new central charges. Probably a very difficult question is to understand what does it mean to condense this non-abelian anion A, which appears naturally when you have a gapped boundary. So to understand what's inside this tube, we must condense A. We know how to do it algorithmically, but not in a very nice path integral formulation. And that's very annoying. And finally, this whole talk, even though I didn't say it very clearly at the beginning, was about bosonic theories. And there should be extensions to spin theories of many things that we found. For those of you interested in the relationship between this talk and Jaume's talk, there is a very telegraphic slide at the end, which you can look up. But I'll just leave this slide for now. Thank you.
Okay, Zohar, thanks very much for this very nice talk. So we have a few minutes left for questions. Are there any questions?
Let's see, there are 19 in the chat.
So I saw a question in the chat. Let me start with that. That was from the, let me see, from the Harvard notes. Let me see how it was. Just a second, there was it now.
I cannot read all of those questions now.
No, but there was a question, but I cannot find it now.
Yeah, I can ask the question.
Oh, just ask the question then.
Yeah, so I wanted to ask, so you have this abstraction to having a gap boundary by evaluating the partition function on length spaces. I just wanted to know if this kind of abstraction, do you know if it generalizes to higher dimensional setups, to higher dimensional TQFTs? Like if I have, like a TQFT in, I don't know, in 5 dimensions, and I evaluate it on a length, I evaluate partition function on a length space, and the phase is non-trivial, then I know I cannot have a gap boundary or not.
I think it's probably a very good question. I was thinking about it while you were speaking. I cannot come up with an intelligent response on the spot. I have to think about it.
Okay, thank you.
The proof that we have for these statements involves at many points properties of 2+1 dimensional topological filters that I'm not sure generalize. So I have to think about it.
Okay, thanks.
Okay, there is a special request from Pedro, Zohar. He says, I would like to see the last slide. Maybe Zohar could show it while replying to the other questions. So maybe you could show the last slide.
There is another question I see, but I cannot come home.
Yeah, there is a question by Ed. Can you ask the question, Ed?
Me? Yeah, my question was, it's a mixture of a question and a comment. You have this equivalent relation involving gap boundaries. I wonder if we can visualize it as follows. Think of the boundary as existing in time. So we're trying to change the Hamiltonian of a system, transforming it from one TQFT to another while preserving the gap. And then a gap boundary suggests that we can transform one into the other, changing the Hamiltonian, keeping the gap. Do you think that interpretation is correct?
I think it's 100% correct.
Okay.
In the mathematical literature, they never talk about a gap. They talk about topological interfaces in topological filters. But the condensed matter interpretation is, of course, that we actually have a Hamiltonian that flows to a topological filter, and we try to change the parameters continuously while never closing the gap. So there is a small jump that I've not emphasized. The notion of gap and topological we should think about them carefully. It seems clear that they are the same, but the notion of gap is something that requires a Hamiltonian, while the notion of a topological interface or a topological boundary does not require a Hamiltonian. It can be phrased purely in the language of fusion categories or braided categories.
Thanks.
Okay, there is also a question from the Weizmann notes. If the two-dimensional CFT with higher central charges have consistent boundary conditions, like it is so for the gravitational anomaly.
I didn't understand the question.
Well, maybe can the Weizmann notes ask the question by unmuting?
Hi, sorry. No, I was trying to ask if the 2D CFT has higher central charges, does this have consistent boundary conditions and all? Like if your 2D CFT has gravitational anomaly, you don't have boundary conditions. So I was asking generalization for the higher central charge.
Okay. You're asking a question about these two-dimensional relative or non-relative theories,
Yes.
whether they themselves have boundaries. Okay. I believe this question should be approached with care, because given that many of these theories where the higher central charges are non-vanishing, or the chiral central charge is non-vanishing, they're relative theories. They require some of them are relative theories. They require a bulk. So the question of a 1 + 1 dimensional, a boundary which is 0 + 1 dimensional, and you have to think about it carefully, because this must extend now into the bulk. So I have to think about the setup in which this question can be asked, consistently. So I don't have anything intelligent to say now.
Thank you.
Okay, are there any more questions?
In 11 dimensions? Oh, I see. Do we know what happens in 11 dimensions? I assume this is in the context of the swampland, which also requires the existence of gapped boundaries. Question? Okay, thank you.
Okay, any further questions or comments? Well, if not, then let's thank Zohar again for this very nice presentation. And